This video covers redox reactions. By the end of this video, you should be able to identify what is oxidized and what is reduced in a redox reaction. You should be able to write oxidation and reduction half reactions, and you should be able to balance redox reactions for mass and charge. So an oxidation reduction, or often abbreviated redox reaction, is a reaction in which one or more electrons are transferred. Oxidation is defined as the loss of electrons, and reduction is defined as the gain of electrons. You can't have one without the other. So if something is losing electrons, something in that same reaction is gaining them. If you have oxidation, you must also have reduction in that same reaction. A good acronym to remember the oxidation reduction reaction pattern is oil-rig. Oxidation is loss, reduction is gain. Oil-rig. So let's take a look at an example. In this reaction, solid sodium metal is combining with chlorine gas to produce solid sodium chloride. So here's our sodium atoms in pink with their happy little electrons. They each have one valence electron. And here's our chlorine molecule, Cl2. It's diatomic. It's also neutral. And so those electrons get transferred from sodium to chlorine. When that happens, sodium gains a positive charge and chlorine gains a negative charge. The other one as well. And we end up with 2 Na pluses and 2 Cl minuses, which as we know will form ionic bonds and give us NaCl. In this case, sodium lost its electron, so it was oxidized because oxidation is loss of electrons. Chlorine gained those electrons, so it was reduced. Reduction is the gain of electrons. We can help identify what is oxidized and what is reduced in a reaction by writing half reactions. So let's take this example. Here we have cesium 4+ reacting with tin 2+ to give us cesium 3+ and tin 4+. The oxidation half reaction would look like this. We're splitting the oxidation from the reduction and writing them separately. So the oxidation would be tin 2+, losing 2 electrons to become tin 4+. That's represented by this half reaction here. Notice the electrons are in the products because they're being lost. That's also a hint that this is oxidation. If electrons are in the products, it must be oxidation because they're being lost. So the electrons are products, like I said, and there are 2 because Sn2+ lost 2 electrons to become Sn4+. Now let's look at the reduction half reaction. Here, cesium 4+ is gaining an electron to become cesium 3+. So in this case, electrons are reactants because reduction is the gain of electrons. And there's only one because to go from 4+ to 3+, you only need to gain 1 electron. Now let's look at how to balance redox reactions. Redox reactions need to be balanced for mass, as all reactions that we've worked with do, but they also need to be balanced for charge. So this is a little bit different than things we've looked at before. So balancing for charge means that the number of electrons lost must equal the number of electrons gained. Notice in the previous example, going back, that was not the case because this was not yet balanced. Tin lost 2 electrons, but cesium only gained 1. So this is an unbalanced redox reaction. So we can do this using the half reaction method. In the half reaction method, you write equations that have electrons or as reactants or products, as we just did on the previous slide. And we separate oxidation from reduction, as we did on the previous slide. Okay, so let's look at the steps for balancing redox reactions. First, we'll write an oxidation and a reduction half reaction. Then we'll balance them for mass if necessary. This step is often not necessary when balancing redox reactions, but it's important to remember to check. Then we'll balance for charge by adding electrons where needed. Then, if necessary, we'll multiply one or both of the balanced half reactions by an integer to equalize the number of electrons transferred. In other words, we need to be losing as many as we're gaining. And finally, we'll add the half reactions together and cancel anything that appears on both sides, which in this case should be the electrons. So let's look at an example. When solid aluminum is placed in a solution of copper nitrate, this redox reaction occurs. Notice I've written this as a net ionic. The nitrate is a spectator, so I've eliminated it. So let's first identify what's being oxidized and what's being reduced. Aluminum is going from an oxidation state of 0 to an oxidation state of +3, so it must be losing electrons. So that's our oxidation half reaction. Copper is going from a 2+ charge or oxidation state to a 0 oxidation state, so it's gaining electrons. That's our reduction half reaction. Next, we're going to balance for mass, but we actually don't need to in this case. One aluminum, one copper, so we're actually all set on that one, but it's always important to check. Now let's balance the half reactions for charge. We'll start with the oxidation half reaction. Notice that right now the left side of the equation has a total charge of 0 and the right side has a total charge of +3. We need to equalize these charges by adding electrons. I'm going to do that by adding 3 electrons to the right side of the equation. That's going to give me a total charge of 0 on the right side, +3 plus -3 is 0, which balances the 0 charge on the left side. So this half reaction is now balanced for charge. Let's repeat that with copper. In this half reaction, we have a 2+ charge on the left-hand side and a 0 charge on the right-hand side. I'm going to equalize that by adding 2 electrons to the left-hand side, which now will give me a total charge of 0 on the left, +2 plus -2 is 0, which balances the 0 charge on the right. So both half reactions are now balanced for charge. Moving on to the third step, we're going to multiply the half reactions by integers in order to equalize the number of electrons transferred. Notice in our oxidation half reaction, we're losing 3 electrons, but the reduction half reaction is only gaining 2. This can't happen. So we're going to multiply the first half reaction by 2 and the second half reaction by 3, which will mean that 6 electrons are lost in the oxidation and 6 electrons are gained in the reduction. Now we can put them back together and cancel the electrons. So there's our oxidation and our reduction. We add them up and notice that we have 6 electrons on both sides, which we can cancel. This gives us a balanced net ionic redox reaction. Here's some to try on your own. First, identify and balance the oxidation and reduction half reactions, then combine them to write a balanced net ionic redox reaction. Notice in C, you're going to have to eliminate some spectator ions before proceeding. Pause the video here, and when you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. A is fairly straightforward, but notice B is a case where we had to actually balance for charge. That's that second step that we often don't need to do, but you should always check for it. And then finally in C, we had to eliminate the nitrate in order to proceed. That brings us to the end of this video. In this video, we identified what was oxidized and what was reduced in redox reactions. Oxidation is loss of electrons and reduction is gain. We wrote oxidation and reduction half reactions, and then we balanced those reactions for mass and charge.